Okay, well, you can hear me. It's wonderful to be back here to see all these young, bright, enthusiastic faces. It's a bit intimidating, to be honest, to be up in front of you, but I'm looking forward to the next hour and a half. It's lovely to see Harry in the audience and some friends and colleagues also. So I'm going to take you on a journey in the next hour and a half into some very exciting science and technology that has had enormous impact, has changed your world. Your world relies on it, and the future is very bright. I'm going to give you some historical perspective. I'm going to give you some stories along the way, and then I'm going to segue into my science and what I'm doing here at the University of Sydney. So, as Chris said, I am Director of CUDOS. This is a centre funded by the Australian Government, so your parents are providing most of our money. Thank you very much. Taxpayers funded research, and we've been at the University of Sydney now for 10 years and are going to be here for at least another 5 years. The title of my talk is Photonic Circuits for the New Information Age, Faster, Smaller and Greener, and that'll all start to make sense as I take you on this journey. I'm going to expect a question every 10 to 15 minutes. And if I don't get a question, I'm going to start asking you questions. Okay, some pretty tough questions. So let's make it interactive. I look forward to lots of tough questions. Before I get going, just a little bit about my history. Chris mentioned that I spent time at Bell Labs, and I think you've heard about Bell Labs in the last 2 weeks from one of the other speakers. It was certainly the premier lab for almost 100 years. It probably is no longer regarded as the premier lab in the world, but it was a wonderful place to work. And this is the lab in New Jersey, Murray Hill, which is about 20 minutes west of Manhattan. And this was the headquarters for AT&T, and then Lucent. I've dropped the Lucent logo here for many years, and my office was down here. And just to give you some context, the transistor was invented there, and Claude Shannon's office was over here. So you might know that name, but all of the theory and understanding of information was formulated and developed at Bell Labs a number of years ago. And so I had an amazing experience at Bell Labs, Lucent, both working as a researcher but being part of industry and part of a leading edge industry at the frontier of technology. And I would say to young people, as you think about your careers, going overseas, working in big institutions like this, very exciting, and working with great people. That's the key to success, I think, in life, is working with great people. And I had the opportunity to work with this very distinguished scientist, Dick Slusher, who's now retired, and gave me a great opportunity to work on some very exciting science and technology. And this was the device that my group invented, developed, and was commercialised and deployed all around the world. And when you make phone calls or use the internet, data's probably bouncing off through that optical fibre off the device that I invented. So I was very proud of that experience. And you can still visit Bell Labs, and there's a little museum here with all of the inventions, the laser, satellite communications, photovoltaics, modern computing systems, and so forth. Okay, so now I spend most of my time thinking about CUDOS, which is, as I said, a national centre. We've got a lovely logo, and the logo will start to make sense. So the O here, the structure is in fact called a split ring resonator. So it's a nanoscale metallic resonator that takes light and induces current and creates a magnetic effect that manifests in material properties that are unavailable in nature. And we're going to hear a little bit about that in my presentation. You can see focusing of light, the 7 universities working together in harmony most of the time. And if you look very closely, you'll see green, and that's a hint of this idea of energy efficiency. So remember, smaller, faster, greener. And you don't need to read all of the details, but I would say that what we're doing is quite entrepreneurial. So we sit at the interface of science and technology. We talk to businesses. We commercialise. We file patents. Our students and our graduates often go and work in industry. And I like to just make a story here because this is me 3 years ago, and this is the group in the front of the school, myself looking very handsome with a brand new suit, the former head of school, the CEO of the ARC, the Dean of Science. And here is Kim Carr, who was our minister, and then he got the boot because the government changed. He was a very popular minister. He was a shadow minister even before he was minister. So he was shadow minister of science 10 years ago. And guess what? He's now our minister again. And I think he'll be here on the university in the next few months as part of the new building project. So it's just an amazing story. I have to sort of explain all the time that he's no longer the minister, but he's now the minister again. Okay, so let me start right at the beginning. You've heard about this week information and data and qubits and light and electromagnetic waves. And of course, when we talk about photonics and optics, we are talking about the electromagnetic spectrum. Okay, and the electromagnetic spectrum extends all the way from gamma rays down here for incredibly small wavelengths, X-rays, and we're familiar with X-rays, of course, the ultraviolet light, which we're all concerned about because that's what gives us skin cancer. And then we've got the visible light spectrum, which is the spectrum that we can see. It's an incredibly narrow slice of the electromagnetic spectrum. It's always amazing to remember that. It's incredibly narrow. And then we have the infrared, which we can't see. It's associated with heat. It's around here that optical communications tends to use those wavelengths at 1.5 microns. We'll come back to that. We've got microwaves, we've got mobile, we've got radio. Somewhere in there we've got terahertz. But it's all electromagnetism, and for the university graduates here, it's all Maxwell's equations. So the equations that describe electromagnetism, regardless of the frequencies, it's the same set of equations. So photonics, for those that don't already know, because unfortunately when I'm out there travelling the world on aeroplanes, in lounges, walking the streets, and someone says, what do you do? And I say, well, optical physics. Often I say photonics, and they don't know what it is. It's really upsetting. The former Minister of Science in New South Wales a number of years ago, when he was presenting, I think it was Tony Stewart, he didn't last very long, in fact, but that's a separate story. But when he introduced me at an event where I was receiving a prize, he struggled with photonics, and he said, this is Professor Eggleton, who's a professor of photonics. So anyway, photonics, obviously, it's the science and technology of generating, controlling and detecting photons, the building blocks of light. And so the name photonics is very obviously borrowed from electronics, which deals with electrons, and photonics deals with photons. And interestingly enough, it's only about 52 years ago, because it was really born with the invention and development of the laser. So if you look back in history, we've had a field of optics for hundreds of years. Physical optics is the idea that you're building lenses and microscopes. And of course, microscopes are hundreds of years old, and if you're wearing glasses, you're familiar with Snell's law and refraction. Photonics and optical physics is relatively recent and is associated with the development of lasers and then optical fibre communications. But in fact, photonics has had enormous impact. In a recent report that came out of the US National Academy on photonics, they point out that photonics underpins $13 trillion industry in the US, which is almost everything. Manufacturing, security, transport, health, defence, data. So photonics is, I've just come back from Taiwan 2 days ago. It was in Taipei in Hingshu Science Park, which is an interesting place where 100,000 scientists and engineers work together. And you might know that Taiwan has an enormous electronics export, $150 billion a year. Our export in electronics is about 5, same population. So they are the champions of displays. That's photonics. Huge industry. Okay, hundreds of billions of dollars. I mean, in my house we've got 4 of these. I don't know. Of course, photonics is now used in the context of imaging, in health, in microscopy, all the time. Photonics is a big part of astronomy. You might have heard, probably not from Brian Schmidt, but if you talk to my colleagues in the School of Physics, we've got some very preeminent professors of astrophotonics. They're using photonics to enhance the optical telescopes they use to discover planets. For example, they're using optical fibres, they're using photonic circuits. Photonics features, of course, in data storage. Your CD player relies on a laser, and we store data. In fact, there was a recent publication by one of the CUDOS groups in Melbourne at Swinburne University that got a lot of press, where they demonstrated a laser-written data storage methodology that's described as 5-dimensional data storage. Okay, they have data stored in the polarization of the light, the colour, and the 3 axes, the 3 dimensions. And that represented something like 1 million times more data density that's available in current CDs. So unprecedented sort of bandwidths and data capabilities. Of course, photonics underpins broadband and fibre communications, and we're going to spend probably a half of this talk discussing photonics, but I haven't had a question. So let's see. When you call someone overseas, how many people in the room think that the signal goes to a satellite? Okay. How many people think it goes through an optical fibre? Right, good. Good audience, good, because I gave a lecture to our third-year students last year and I asked the same question. Most of them thought it was the satellite. I mean, this is not the case. We moved on decades ago from using satellites for communications, and the punchline is that they're not particularly good at dealing with high bandwidths. We're going to use optical signals. We're going to use photonics. The bandwidth capabilities of fibre optic communications are just amazing. Okay, so this is a sort of 30,000 kilometre view of the world. It's actually a few years old. It's the optical fibre submarine system. Submarine doesn't mean submarines, it means underwater. This is a snapshot of what the global communications network might look like, and that's optical fibre. Okay, it's laid out all over the place. This is just oceans. Yes?
What exactly is high bandwidth?
We're going to get to that. Yes?
When you say underwater, does it mean underground?
It means these are cables that are about that thick. They're thick because they have protective coating, because the fibres themselves are the size of my hair. I'm going to show you that in a few slides. But they need to be solid because sharks, actually, you don't want to have to go down to the bottom of the ocean, but they literally sit on the bottom of the ocean. They do, across valleys. And you'll see these incredible ships on the Discovery Channel. There's a great documentary on this ship that goes out there. It's the size of a liner. And its job is to go out there and bring these cables up, open up these massive, thick things, go into the middle and find these 2 tiny fibres like my hair, find the break and reconnect them. And it's very expensive. You don't want these fibres to break. When I talk about high bandwidths, I'm talking about bits per second. I'm talking about the data rate. And you're probably calibrated to the bandwidths that you get at home when you do your broadband, and you're probably familiar with megabits per second. That's 1 million bits per second. A bit is like a 1 or a 0. When I talk about high bandwidth, when I talk about my research, I'm talking about terabits. So how many zeros are there in terabit? How many? 9, 12, 50, 12. The record, which was broken last year by the Japanese, for a fibre optic demonstration, one single fibre is a petabit. How many zeros? It's just ridiculous. 15 zeros, okay, in one single mode fibre. Yes?
Should you create better fibres with higher bandwidth, seeing as these older ones are already laid out, how do you make your...
That's where we're going. That's where we're going. Okay. All right, so let's look at this. And I like to draw the analogy that these networks are like the freeways and the highways. If you like, it's the same problem. It's bottlenecks, it's capacity, it's speed. The lanes of the highway are sort of like the different wavelengths that we encode the data on. I'll introduce that concept in a bit. That's called wavelength division multiplexing. And the real bottleneck is, in fact, the point is actually to say, in general, the fibres in the ground have the capacity, we're just not using it. So the bottleneck is getting the data in and off. That's the bottleneck. The bottleneck is to take advantage of the enormous bandwidth that the fibres offer, because you're operating at a carrier frequency that's 100 terahertz, okay, rather than in contrast with microwave frequencies where the carrier is
megahertz. So you have available to you hundreds of terahertz of bandwidth, potentially. But you've got to get it into the fibre, you've got to get it off the fibre, you've got to build switches, routers, logic circuits, so that you don't end up with this type of scenario, and that's the bottleneck. It's really getting the data onto the channels and off the channels. And that's what our research, that's what CUDOS has been focusing on for the last 10 years. And it's where our research focuses on nanotechnology, building a photonic circuit that's faster, smaller, and greener. And I'll show you, not only have we developed some world-leading technology that is going to make the internet faster, essentially, but it's having applications in other areas, in quantum information, in sensing technologies, defense, and all of these other areas. And I like to say that photonic circuits, photonic chips, and I'm going to hand one out at some point if I don't forget, it's the paradigm for the 21st century. Optical fibres, 20th century. The 21st century, we're focusing on nanotechnology and photonic circuits. Okay, so let's go a little bit further, a bit of history. This guy, Charles Cowell, who still lives, he's an old gentleman, back in the late 60s, was working at Harlow in the UK and stumbled across this fascinating proposition that he thought, well, in fact, if I take glass, just basic silica, if I melt it and I draw it into a strand of glass, I will be able to guide light through total internal reflection, and he suggested that the loss of these fibres would allow transmission over 100 metres. And that was a revolutionary paradigm-shifting breakthrough. It was so significant that a few years ago it was recognised with a Nobel Prize in Physics. Unfortunately, it was 43 years after the invention, so that makes me think that I've got a few years to wait based on that example. And unfortunately, he had mild dementia at the time, so he was not able to present at the Nobel Prize ceremony. His wife did. But it is a wonderful story. Of course, what I said before, you might have stopped and said, hang on, 100 metres? That's nonsense. In fact, that was the amazing thing. After this initial eureka moment breakthrough, he postulated that we could send data on a laser through 100 metres. Corning, in New York State, in the lovely town of Corning, demonstrated that fibres could be made very low loss. And geez, they were pissed when they didn't win the Nobel Prize. And so the rest is history, as we're going to see over the next hour. So this is Charles Cowell, this is his wife, and I've met Charles, and I've met his wife. And this is him back in the late 60s, developing the first glass waveguides for fibre optic communications. So it's interesting to reflect, because when the Corning folk were so upset that they didn't win the Nobel Prize, there's been a lot of discussion about whether it was obvious, whether that Cowell's breakthrough was the real breakthrough, or was Corning who reduced it to practice, who deserved the recognition. And it's interesting to reflect, because it wasn't obvious at all. If you look back in history, we had the laser invented 53 years ago. It was a solution looking for a problem for a long time. And the idea of sending signals optically had been around for the ages, and I'll get back and show you that in a while. But these are some of the architectures that were being considered by Bell Labs. Free space communications. Let's take a lamp, a broadband incandescent lamp, and modulate the intensity and encode some type of digital signal on the lamp. Maybe use a lens and have a photoelectric cell. Well, that might get you across the campus and might have a data rate of a few kilohertz. But it won't get you much better than that. It's the idea of building a guide with lenses and a lamp and photomultiplier tubes using mirrors. At some point there was a demonstration in New Jersey along the New Jersey Turnpike where they built one of these links, and they actually had a vacuum tube with lenses every 100 metres, recollimating to the extent that they could to send this broadband incoherent signal. It only went a few hundred metres. And so you had gas lenses, and of course the key breakthroughs were, as we've discussed, the optical fibre and the laser. These two incredibly exciting inventions. Yes? Oh, it's an avalanche photodiode is a photodiode that relies on cascading electrons, and it enhances the sensitivity of the detector. So it's a specific type of photodetector that converts photons into electrons. So the concept of a photodiode is to take an optical signal, photons, and rely on some photoelectric effect in the semiconductor to generate electrons, and the electrons can then be detected as a voltage, which you'll see on an oscilloscope. Good question. Okay, so a bit of the physics. Now, I think you've already heard from my friends Philip Russell and Tanya Munro. You've heard about optical fibres. So you know that the concept here is to take a glass waveguide and you've got a core and a cladding. And the physics is very simple. You rely on total internal reflection. The glasses that are used in modern fibres are so pure that if I had a 100 kilometre thick block of glass between you and I could see you on the other side. Okay? Think about that. They are so pure, the contamination, the impurities are at such a low level that the loss is at the level that I don't need to amplify for 100 kilometres, in some cases even more. And it's simply total internal reflection. Remember, if the index of the core is larger than that of the cladding, the light is trapped and it won't escape. And the only mechanism for loss is somehow scattering off the impurities that might be residual, that you just aren't able to remove. And you can propagate through hundreds of kilometres of this fibre, and then you have to optically amplify. So schematically, what one of these communication systems looks like is that you have a bunch of lasers. They're at different wavelengths. So rather than simply modulating at a faster and faster modulation rate to increase the data rate, we use a very elegant concept which is wavelength division multiplexing. And so you might have 4 lasers that emit slightly different frequencies. Okay, each of these lasers is modulated with data, 1s and 0s, as fast as you possibly can. And they are multiplexed, it's an easy word, onto this light pipe. We call them light pipes, really, in the business. You say a light pipe. It's a single mode fibre. And ideally, these different wavelengths don't interact. Photons don't interact, do they? Photons don't interact. I'm going to tell you something else in about 15 minutes. But photons don't interact for now, believe me. Okay? They don't interact. They will sail through the fibre. They won't interact. And at the output, I have the same information, and all I need is some type of thing that separates the wavelengths. Now, these things at the front and the end, turns out they were non-trivial. And here's the question. How would you imagine separating these different frequencies? What do you think you would use? It's a type of concept you come across in high school physics. What would you use to separate these different colours? Because what I've got to do is take these 4 different colours, separate them spatially, and send them onto these photodetectors, where the photons generate electrons to generate a voltage, which gives me then a 1 or a 0. What would I use? Yes, sir. Prism. Excellent. What else could I use? Yes. Filter. I want more information, please. But what would the filter be based on? What type of filter? How would I realise the filter? The prism is indeed the obvious way to do it, because different wavelengths will refract at different angles, and I spatially separate those signals. But what's another device structure that we come across? Yes? Ooh. More information, please. Well, what I'm talking about, I want to separate these wavelengths. I'm going to use a grating, a diffraction grating. Diffraction grating will take different colours and diffract them. And those were enormous challenges in the 90s. And that's when I was at Bell Labs, trying to come up with simple ways of getting these different frequencies into this light pipe and separating them at the end. And now, there are probably 1 million of those that have been made out there. And they're based on prisms, they're based on gratings. So the last concept in this initial preamble is just to remind you and point out that we're talking here, this is wavelength, and this is 1.2 microns. Remember, visible light is down at 500 nanometers, 600 nanometers. We're up in what's called the near infrared. And it turns out, the black is the loss of the fibre. It's in a funny unit called dB per kilometre. And just to calibrate you to that funny logarithmic unit, 10 dB means that you've lost a factor of 10. So if it was 10 dB per kilometre, it would mean the signal intensity drops by a factor of 10 after a kilometre. But the number here drops to about 0.25. Okay? That implies that over 100 kilometres, I'm up at about 20 dB, which is a factor of 100. And remember I talked about seeing you? My eye is sensitive enough to see 1/100th of the intensity that's in this room. So if I had to look at you and it was cut by a factor of 100, I'd still see you. And that's sort of the length scale over which signals are re-amplified. This is a peak associated with water contaminants in the fibre, which turns out can be removed. And the red signal here, anyone want to have a stab at what that represents? It's sort of on the slide anyway, but yes. You can read, good. Well, this was another one of the great inventions of the 90s, and my friend Dr. Simon Poole, who was one of my mentors, who is the chief scientist at Finisar, was part of the team that invented the optical fibre erbium-doped amplifier. A revolutionary concept that could take light in an optical fibre, send it into a very special doped fibre with erbium ions in it, pump it with a laser beam, and it would amplify the optical signal. So for the first time, signals could be amplified, which meant after 100 kilometres, I don't have to then digitise that electronically with a big repeater that size of the room. I just amplify it optically. Turned out the optical amplifier that was invented had a gain spectrum that looks like this. Tiny, tiny slice of the overall spectrum. And even today, all of our networks rely on these amplifiers that are 20 years old because they're cheap, they're reliable, and it gives us about 5 to 10 terahertz of bandwidth. And that terahertz of bandwidth, roughly speaking, tells you how much data, the data rate that you can squeeze through this fibre. Except for the fact that I told you the record is a petabit. And the way they got to a petabit was tricky. They took advantage of the entire spectrum, say 10 terahertz. They used concepts from mobile technology where they relied on not just 1 and 0, but multiple levels of encoding. They had a fibre that had 20 cores in it. Fancy that. And they relied on the polarizations. Okay, and from all of that, they achieved a petabit in a single mode fibre, in a single fibre the size of my hair. Now, I've seen a few hands up. Yes, this lady here. There is distortion and there's noise. The amplifier introduced what's called amplified spontaneous emission. These atoms get pushed up, they emit photons, they amplify, but there's a lot of noise. And that noise is a real problem. It turns out it's one of the drivers for our research is noise associated with the amplifier. So as you amplify, every time you amplify, you add huge amount of noise. And these ones and zeros, eventually the zeros fill up with noise. Big problem. And we're going to talk about that. And the solution is to do what we call regeneration. You have to regenerate the signal to get rid of the noise. And that was a $10 billion problem. Yes, up here. No, going over here. Young man, yes. Well, that's a long question to answer, but I will tell you, I'm not a social scientist. I don't study human behaviour and how societies evolve, but there are people who do that for a living, and it's really interesting to see that over the last 50 years, there's been a Moore's law for bandwidth. You're all familiar with Moore's law? There's been a Moore's law for bandwidth, and it's never slowed down. Okay, it's doubling every 18 months. There's no hint of it slowing down. And some scientists have published in Nature, they think that the human individual, probably at around 100 gigabit per second, the brain says no more. Okay, that's to an individual. Okay, one person. Now, times that by 20 million, that's sort of where the petabit number comes from. There's no hint of it slowing down. In your lifespan, for sure, you will be having more than 10 gigabit into your home. Okay, the NBN has already talked about gigabit per home. But that's to the individual. That's not the backbone. That's to the home. You've got to think about these big freeways that link the cities. Just a quick story. One of the breakthroughs that we reported 4 years ago was a demonstration of a switch at 1 terabit per second. It was the first demonstration, and we got huge amount of media attention. It was on the page 3 of the Herald. It was embedded in a story about the release of the iPhone. Okay, fancy that. Amazing. So I was on the radio all week. We were in Catalyst. Globally, we had a huge amount of visibility. But the story got distorted along the way because, of course, we weren't talking about a terabit per second into the home. This is about terabits in the backbone. And they asked an Oxford University professor what he thought about a terabit per second as in the home. And so he started to come up with all these apps and how a family would use a terabit per second, which was a bit silly because I don't think we're ready for that type of bandwidth yet. But look, nobody's ever been able to foreshadow or predict. I mean, 20 years ago, walking the corridors of Bell Labs, there were people who didn't believe in a gigabit per second. Okay, they really didn't. There were people who just couldn't see beyond having fibres that transmitted hundreds of megabits. People who didn't believe in wavelength division multiplexing. People who couldn't, and even the politics in Australia, as I'll get to, you know, we've heard the debates between the two parties. You know, you believe or you don't believe, but nobody's been able to predict ever. Okay, so let me get I'm going to go through this story a couple of times, but where I'm going here is that photonics enables bandwidth. And what our researchers really be focusing on is taking photonics to the next level, not only for light pipes, but we're going to deal with this bottleneck that I alluded to earlier, of getting the data onto these channels, onto these light pipes. And the way we're going to do it is to use photonics and not electronics. It's all about photonics. And we're going to build optics on a chip. We're going to integrate sophisticated nanotechnology onto a chip. And I'm going to show you that, in fact, photons do interact with photons sometimes. And we can do that on a chip. And that allows us to do this unprecedented level of processing. Okay? So this is all part of a revolution that's very much like the revolution we saw in electronics. Okay? It took 30, 40 years in electronics, Moore's law. We now have these amazing iPhones and technologies, and it took decades. It took trillions of dollars of investment, R&D, around the world. But now we have these incredible microprocessors and nanoprocessors, and I guess what we're trying to do is a very similar type of paradigm-shifting, revolutionary research that will create photonic all-optical processors. So, you know, it is very much like going from here, one of the early computers, and Harry, this is probably not you, but this is looking like one of the early computers in the School of Physics, and this is what you might have on your desk. And that took decades, okay? And along the way, it changed the world. So what this is a photonic circuit. And now I've got a few things. I'm going to pass them around now because I can see a few people nodding off. And that's absolutely not allowed. So I'm going to pass this around. And there are two things to say. Don't touch it. Don't lick it. Okay? Because there are always chemicals on these devices, and I don't want you to do anything silly. And don't put your fingers on it because they're actually sharp. There are two chips here. One is made out of a chalcogenide glass, and another one is silicon. They're photonic circuits. And if you hold them up, you get the right angle. This has got tape on it, but if it falls out, just pick it up, but don't turn it upside down. You'll see the wires on it. You can see a fingerprint. Someone's touched it. And this is silicon. And on this, you won't see it, but there are literally millions and millions of holes that have been etched into this circuit. So why don't I pass that around, and I'd like it back. Now let's see if my little movie works. This is an artist's impression of a photonic circuit, and what you see here is at the bottom an optical fibre, and you see little bullets of light. They're not actually photons, but mind you, when I get to the end, you'll see that we're actually doing single photon photonic circuits. So they could actually be individual photons. And each of the little elements on this circuit is one of the building blocks that we've been working on in my group for the last 5 to 10 years. And you can see, in fact, this is on the web. We can actually download this and you can run this for yourself. But this is a prism. We talked about prisms. This is how you separate wavelengths. But notice this prism is made up of hundreds of little tiny holes. This is called a photonic crystal. And this prism is about 10 microns. See how it separates those colours. So let's see if we click out. And I'll show you one other, and that's an optical buffer. That's a really hard problem to solve, the optical buffer. How are we going to build an optical buffer? We're going to try and slow light down. We're going to use some type of grating effect. And let's see what happens here. The light comes in at the speed of light, and it slows down. And we've been able to slow light down on a chip for the first time and achieve some remarkable processing capabilities and use science. So the point of this chip, in fact, it's a photonic circuit. Question? Yes? That's the million-dollar question. As I'll show you, people have slowed light down to bicycle speed. Okay, but they've done that in a gas that was at nanokelvin temperature over a bandwidth of about 1 kilohertz. And so what we've been trying to do, and we're going to come back to this point, we're trying to slow light down not as much, probably 1/10 of the speed of light, 1/50th of the speed of light, in a regime where we can actually slow down bits of information enough that we can build a buffer, okay, at room temperature on a chip. Yes? How come we need a buffer? What's a buffer? Well, it's a good question, and I haven't introduced the concept yet, so it's a fair question. Data networks are very simple. Think of the highway analogy. Think of the highways. When I drive down to Canberra, I'm in the right lane and I'm doing 116 because that's kind of where you think you're okay. And then every once in a while you get to an intersection and there's new traffic and I have to get out of the way. Okay? Now in electronics, in information networks, we have the same issue. And the way you deal with that is you buffer. Okay? You have to take that data and you have to slow it down and store it so that when you send it off again, it's synchronized and it sits in a slot where it's okay. That's a buffer. So buffer is storage. It's really the idea that you can take data and store it for some time. In electronics, buffers can store data for a long time. In optics, this is a really hard problem. Yes? Aha. Yes. We're going to come back to that. One of the problems is we did it, and people have done it, and this was a huge area of research. DARPA put $50 million into this in the US. Do you all know what DARPA is? Yep, very interesting organisation. They invested $50 million into a DARPA program in the US, and they ran into a problem. They could slow light down, but the pulses spread. So we're going to come back to that. Let me get back to that. Yes? Because... I don't know. When you say why not, I'm asking you why. So you're saying why don't you... Okay, you're saying why don't you go electric? Good point. That's a good question. Fair enough. Good question. Because we're going to do this 100 times faster than electronics can possibly cope with. We've got two types of concepts here, and I know this is confusing. We've got the speed, the velocity of the information, and we've got the speed, which is the data rate. Don't confuse them. The data rate is how many bits per second. We're terabits per second. 12 zeros. Okay? And we're going to slow the data down. And that's faster than electronics can possibly keep up with. And we're going to slow the data down optically because we can't do it in electronics. Okay. The nice thing about this is we're going to piggyback and leverage the $1 trillion microfabrication for electronics industry. So a lot of our research piggybacks on the semiconductor fabrication capabilities that have been developed over the last 40 years, Taiwan, Singapore, Korea. We have one in Sydney to make microelectronic circuits in silicon. A lot of our research and one of those chips is in silicon. And of course that's very exciting because at the University of Sydney, if you've walked in the school, you'll see a new building, the Australian Institute of Nanoscience, $90 million. Thousands of square metres, and in the core of that building is a clean room for nanolithography. The same type of clean room that you'll see in a semiconductor foundry in Taiwan to fabricate chips. We're going to use these chips in photonics and quantum science. we're going to have all of these wonderful capabilities. And anyway, this is an old slide, but we've already demolished A29. That was a highlight, that's for sure. And that'll be open in about 2 years. And I think you've all been into the school in the last 2 weeks. Yep, so you've seen all of that. Okay, so a little bit more. Bit of history. So we've been communicating for a long time. And this is one of the early optical communication systems. It's the semaphore. Okay, and I've actually got another movie. Let's see if this works. What's it all about?
C'est des potes. Message to Joséphine. I am not wearing anything either. Ah, Joséphine. If only we had broadband.
This was prepared. Okay. Harry might remember this was prepared for a dinner I spoke at, probably 2005, and I went overseas and I asked my students and postdocs, look, I need something really good, entertaining, and I came back, and these are my former student and my colleague who's still in the school, and that was actually on the roof of the school, as you know. So let me show you one other. Let's see if this works.
C-U-D-O-S. Monsieur, the report. CUDOS? What is CUDOS? What is CUDOS? I do not know, monsieur. What is CUDOS? I don't know!
So look, we've been communicating for a long time. Let's just go through this. So we've had ponies, you know, these were some of the very early low data rate, bit rate experiments. We've got telephones, of course, but now we live in an amazing world where the internet, the web, is changing the world. It affects politics, it affects lifestyles, health, education, entertainment. It's mostly good. I think it's good for society. I think there's compelling evidence that society is benefiting. There's more wealth, there's more health, there's more happiness. We know more about the world. It keeps us honest. It's a more transparent world than it used to be. And nobody anticipated any of these apps. Okay? Google came out of nowhere. Facebook came out of nowhere. They were not anticipated, and we can't anticipate what's coming next. And as I mentioned, the Moore's law applies beautifully to bandwidth. This is an old plot, but it shows the bandwidth. The scale is not particularly important. This is exabytes. I don't even know how many zeros there. With exabytes, it might be 18. Point is, you can see the traffic is going up. And you can see it's internet, it's mobile. And of course, when you use your mobile, and how many here don't have a smartphone? Oh. Okay, when you use your mobile, you're communicating via microwaves, but very quickly, the signal goes optical. Okay? Microwave, optical complement each other. It's not a race against each other. They are working together. Microwave is only for short distances, low bandwidth, because the carrier frequency is only tens of megahertz, 50 megahertz. Optical, 100 terahertz, long distances, huge bandwidth, but it's not, it's wired. It's a wired system, okay, as opposed to wireless.
Of course, in Australia we have the NBN, very exciting, and photonics is the key technology. That's at the heart of the NBN. It's fibre optics, it's lasers. We're talking about fibre optics to every home, and it depends who wins the election. It might be to the home, it might be to the end of the street, but regardless, it's a multi-tens of billion-dollar investment in Australia, and it's good. It'll be good for the economy. It will pay for itself in the long run. It will stimulate innovation. It's a tremendously exciting project, and we've got to keep the politicians excited about this. We've got to keep them on track, because I'm deeply worried that they'll lose the inertia. And look, Australia's not even in the top 10. We're about ranked 15. I travelled to Taiwan, Singapore the last few weeks. I'm going to Korea on Tuesday. South Korea is number 1 in terms of bandwidth. Singapore has almost gigabit per second per home. Okay? We're okay if we live in the city. I don't even get 5 megabits, and I live about 500 metres from here. Okay? And I don't get 5 megabits. Every 6 months I go to Brunswick Heads, where my wife's family is, and they have dial-up speed. That's pretty exciting. But they say, my mother-in-law says, no, look, you go down to the Brunswick Heads pub, which is a lovely pub on the beach. They have a Wi-Fi, so I go down and plug in and I get about 40 kilobytes per second. But the cousins who live in Mullumbimby have broadband, and I get about 100 kilobytes a second. So it's all Australians, and that's what's really exciting about this NBN. And the Labor perspective, at least, is 40 billion. The Liberal coalition, maybe 2/3 of that. They're both good propositions. Okay? It depends almost on your philosophy, which one you believe in. Should the users pay? Should it be all top-down? I think it's exciting that both governments embrace broadband, and it's all about optical fibre and photonics. So let me carry on. Few things have changed in the last decade that weren't issues. One of the big issues that changes the way we think about communications and data and bandwidth and energy is that with all these online functions like Facebook, like Google, like YouTube, Twitter, the photo apps and all of these other things that I don't even keep up with, associated with them are these massive data centres. I don't know if you've ever seen these. They're in North America, they're in Europe, they're in Asia. It turns out in this report that I mentioned before about from the US Academy, one of the issues that was flagged is that strategically the US is responsible for almost all of the world's data. They have most of the world's data centres. Most of the world's data goes through the US. So interesting security issues, interesting strategic issues at play there. But these data centres are as big as the School of Physics. And they comprise tens of thousands of servers that are connected via optical fibre. Well, this is an old one. This is not optical fibre. You can see the nightmare of communicating these different 10 gig servers. And this is where all the data is stored and processed. So when you go on Facebook, you're actually accessing a data farm probably that sits on a river. Why does it sit next to a river? Cooling. Huge amount of power required to keep these systems cool. In fact, I heard a fascinating talk last week. The biggest data centre in the world has been built, where is it? Norway or Sweden? Up near the Arctic Circle. Sounds crazy. And of course, there's an obvious reason for putting it there. It's cold, okay? Really cold. And these data centres are now generating CO2. Okay? A significant fraction of the world's CO2 emission are coming from the internet. Now this is a scary plot. It's a few years out of date, and I'm pretty sure it exaggerates the point. But it shows you energy consumption. This is a Japanese perspective from their national lab, IST in Tsukuba. That's like the CSIRO of Japan. And it's plotting the energy consumption of IP routers, okay, as a function of time. This is internet traffic. You can see 2010, it's about a few percent of the total energy budget. But what happens here? What happens right there? It's hard to believe, but it's basically, this plot says the entire energy budget of Japan will be consumed by IP routers in 2020. Okay? Now, I think this is exaggerated, so don't take a photo of this and go off and tell the media that Eggleton said this, because this is a few years out of date. There might be a factor of 2. Okay? Still terrifying. And so this has really rallied researchers around the world. It's introduced an entire new degree of freedom to photonics and communications, which is energy. Can we be more energy efficient in the way we transport, process data, store data? Are there clever ways that we can do it more efficiently? There's more energy consumed in the internet than there is in the entire airline industry today. Which industry is growing faster? Communications is going at Moore's law. It's doubling every 18 months. Okay? Now the good news is, and this was before the tsunami in Japan. Okay? If you go to Japan now, pretty a bleak place. Every employee has to pay a tax to rebuild. The air conditioning is turned down in the middle of summer because they don't have enough energy. So buildings are kept at something like 28 degrees Celsius. Because they're winding down their nuclear reactors. Okay? So this is a global issue. Now, at the same time, big picture, one of the emerging themes that's really exciting is that photonics is now being considered as a key solution to communications within computers. Okay? The idea is that we saw the data center, which was connecting computers. Interconnects is the idea that I'll need to connect the chips within a computer. I already communicate within my computer. There's a huge amount of communications within a computer. And essentially there's a bottleneck. They're running into a bottleneck. It's a power. It's a dissipative effect associated with copper. It simply doesn't have the bandwidth. And so photonics is being considered as a key solution for interconnects. Next generation computers will have photonic circuits integrated into the computer itself for the communications. And beyond that, there's the fascinating proposition that you'll have optical wires integrated onto the silicon chip itself to communicate within the chip. Okay, this is real. This is work that's been done by Intel. Here's a simple example. They're already communicating between computers with optical fibre. You can already buy products that are optical fibres for Ethernet. You don't even know it, in fact. You plug something in, and it's an optical fibre connecting your storage to your computer, and it's optical fibre. And the next generation is within the computer. That's starting to happen. Yes?
Sorry, does this help with more for energy consumption or more for increased performance?
Both. I mean, I've seen some amazing predictions that show that the heat generated in the cores of these computers is approaching, meltdown. It really is approaching meltdown. And they're really coming up with radically new ideas. This is not radical. This is actually mature. IBM, Intel, Sun, they've got massive programs in this. Okay? Yes? Yeah, that's a great question. It's really hard to do that in silicon. You can't make silicon layers. It doesn't have a direct band gap. And that's been one of the grand challenge projects. How do we generate the photons in the chip? So what we do at the moment is we generate the photons off the chip. Okay, and then we have them on, the photons are on the chip, and then we modulate the photons on the chip. We communicate within the chip. But generating photons in silicon is hard. Now, there was a Nature paper last week, it turns out, by Susuma Noda at Kyoto University, who is just tremendously impressive, who demonstrated a Raman laser in a micron-scale silicon photonic crystal. Too much jargon. But the point is that he made it laze, but the problem is it was optically pumped. Okay? So he had to put photons in to generate new photons. So it is a laser in silicon, but it's optically pumped. Electrically pumping is almost, no one's done it in silicon. And there'll be a Nobel Prize if you can do it. Yes? Well, the whole point is, good question, the whole point is to not sacrifice anything else. Okay? And the nice thing is silicon, it turns out, is compatible perfectly with photonics, but you need the third dimension. So what we're going to do in silicon is have a third dimension. We'll have a photonic layer and we'll have the electrical layer, and they'll communicate Okay, but you can't compromise the CMOS fabric for the electrical logic circuits. We're not going to do logic with optics. We're going to communicate with optics, but you can't compromise. But it'll make it faster and more energy efficient. One last question, this gentleman here. When can we do logic using optics? That's a good question too. I'm not a believer in that anymore, and in fact I never was. It turns out that was a huge area of research in the 80s when I went to Bell Labs, so-called optical computing, optical logic. And that's not what this is all about, even though I'll show you that we can interact with photons, and I can make a photonic transistor. And there was another paper in Nature last week, someone did a photonic transistor. But the problem is very simply that the wavelength of light is much bigger than the scale of these transistors. Okay? So there's no compelling case to build sequential logic with optics, because you can't do it efficiently. And it turns out there are first principle arguments that people have published that show that in the limit of only a few logic steps, optics is more energy efficient. But beyond about 4, electronics is more energy efficient. So everything we talk about is only a few logic steps where it is more energy efficient, but not beyond that. You can't compete with electronics because there's 1 million transistors in your circuit and your chip. Now, we are routinely doing optical logic in my lab, but we're usually doing 1 or 2 logic steps only. And the reason we do it is because it's much faster than electronics and it is more energy efficient. Okay, but we're not going to build a computer. We might do something related. We might try and build a quantum computer with photons, with qubits. But there we may only need 20 or 40 qubits for reasons that you would understand if you went to David Riley's lecture. Yes? You're always going to have electronics there, and you're going to work in harmony with electronics. Electronics does its job very well for logic, low bandwidths, tens of gigahertz. Optics does its job for transport, enormous bandwidths, terabits, petabits, exabytes, okay? And we're going to try and use photonics to get the data into the fibres, into the light pipes, and process them when we can do it better than electronics. But we're working with electronics, and at the end of the day, we've got to communicate with electronics anyway, because the world we live in is electronics. The computer that you stare at, the iPhone that you read is electronics. Mind you, there's a hell of a lot of photonics in this, by the way. Just as a side. Text message. Photonics is used almost at every step. The display is photonics. Okay? The chip was made using laser. Laser machining was made to do the fabrication of the outside board. Okay? And you're using optical fibres to communicate. So a lot of photonics. But at the end of the day, it's ones and zeros that we deal with, and it's electronics. Yes? Well, the point is to do it more energy efficiently, to do the communications. That's the promise, and to do it faster. Let me keep going. So this is not just me speaking. This is a global trend. This is a report from Intel, and they reported here a 40 gigabit per second silicon photonic chip transmitter with hybrid silicon lasers and modulators. The lady here asked that brilliant question. The word hybrid implies that the laser is not in the silicon, because you can't make silicon lasers. And these are the devices. This is optical fibre, and this is the silicon chip. And so it is about smaller, faster, and greener. And what we're really here looking at in a whole bunch of different contexts is reducing footprint and reducing energy consumption. And let me segue, because I want to get on to the science that we're doing here at Sydney. And I guess I don't want to confuse the message here, because we're not trying to build an optical computer. We're trying to build on a chip all optical processing to do a small number of logic steps much faster, much more energy efficient, so that we can process information more efficiently, more swiftly than electronics can in the context of communications. And along the way, we're going to build the photonic circuits that will allow for communications within these computers. But the general concept that I'm focusing on, the science that I do, the physics that I understand better than anyone else in Australia, I might claim, is to exploit nonlinear optics. We're going to talk about nonlinear optics, okay? And I'm going to show you that with nonlinear optics we can have an ultra-fast light-light interaction. We can interact photons with photons. I'm going to show you that we can put waveguides on circuits that create wires for light, and I'm going to talk about photonic crystals and possibly metamaterials, depending on time, which have exquisite properties that will allow us to control light in very exquisite ways. The lovely word exquisite, you can only use it once in a talk.